Hi everyone, it's an honor to be invited to the third AV Vision workshop at ECCV 2022. My name is Wei Liu. I'm currently the head of machine learning research at Nuro. Today my talk is achievements and open questions for autonomous driving. So for those who don't know about Nuro, let me play a short video to introduce Nuro. So in a summary, Nuro, we are a robotics company where our vision is to better everyday life through robotics. And our first product is to build this customized vehicle as shown in this image, where we deliver goods from store to your house. And we believe that by removing human inside the vehicle and simplify the problem and also deploy the product into the real world and improve people's life sooner. And we also believe that by removing person in the vehicle, we can also deploy machine learning solutions on it faster. And in today's talk, I'm going to talk about the three major problems that are faced in autonomous driving. The first is about perception. So basically, it's taking any sensor input and we want to understand what is going on in the environment, such as to detect this person. And then after we detect all the objects and track all the objects, we want to predict what the future for each of the objects looks like. And finally, after we have the perception and prediction, we also want to plan a safe and smooth trajectory to navigate in the environment. So this is outline of my today's talk. I will first talk about the achievements for autonomous driving, especially the machine learning efforts at Nuro in the last 6 years. Then we'll also discuss some open questions and challenges for autonomous driving. And finally, I will have a short conclusion for my talk. So achievements for the autonomous driving. I think it all starts from AlexNet in 2012. Basically, it's a step function change for the computer vision community where it just beat all the previous computer vision solutions. It changed the paradigm of how people think about solving computer vision problems. Before AlexNet, people are using heuristics and expertise to design, to extract and design features for each particular problems. After AlexNet, the thing called feature learning. So basically you can now, instead of using manual extract features, you can learn all the features through convolutional neural networks or other kind of neural networks. And of course, after AlexNet, and we just say revolutionary and rapid improvements, such as classification, we have VGGNet, GoogleNet, ResNet. On detection front, we also have a series of the famous region CNN, RCN, and also the follow-up of fast and faster RCN, and also the single stage of these object detectors such as Nuro and SSD. On the semantic segmentation front, we also have like the fully convolutional network, UNet, etc. And for instance segmentation, we have mask RCN, etc., which just achieve tremendous of impressive performance for the instance mask estimation, and so on and so forth. So basically, like from 2012 and 2015 or 2016-ish, people just, this deep nets and automatically feature learning just revolutionized the computer vision community. And yeah, it seems like computer vision is solved at this moment. But all the previous thing that I talk about is mainly focused on the 2D domain, basically 2D image. But how about 3D? Because for autonomous driving to apply this kind of machine learning technique, we need to understand the 3D location, 3D environments in order for the self-driving autonomous driving vehicle to navigate in the environment. So the first work that I think is a very fundamental kind of change, at least at Nuro, I think is a step function change for us, which is called the Frustum PointNet that we published in around 2017. And the idea is quite simple. I mean, it's very similar to the famous mask casting method, where you can take any of these your favorite 2D object detector, and you can do object detection on top of the image. And after you get this detection, for example, the red box, and you can calculate the frustum space that was defined by this 2D box. Basically, you try to get all the points within this frustum, like that was identified by the red region. And afterwards, after you get all the LiDAR points, you can apply PointNet to classify each of the points to see whether it's foreground or background. So this is very similar to the mask casting kind of work, where you first do 2D detection using the 2D detector, and afterwards you do ROI align, and then to extract all the pixels within that detection range, and then you do classification. You do per pixel classification, but here we do per point classification. So after you classify the foreground points, and then you apply some regression head to regress the 3D bounding box. Of course, there's a lot of tricks on how to make it work, but for more details, you can refer to the paper. I think the other one, I think this is also very fundamental, which is called VoxelNet. So instead of like viewing the 3D object detection from perspective view, it actually try to do detection from top-down view. So for example, here is a top-down view representation of how the LiDAR points look like. And in here, particularly, like we only use LiDAR points. And yeah, it's a paper published from Apple, I think around the same time as Frustum PointNet. And like for these LiDAR points, right, like the pose, everything, you can just do some geometric translation, and you can accumulate multiple frames to just make your LiDAR points be more, dense, and you can get more information. And also, like for moving objects, you can get this kind of like the history of all those, and you can use those kind of things to do prediction, or like to estimate velocity, for example. And after you accumulate those, the VoxelNet was basically trying to discretize the top-down view into multiple grids. And then for each of the grid voxel that we called, or pillar or whatever, and you can try to use PointNet to extract features to represent each voxel. And again, like it's basically everything is like the features are fully learned. So with all the previous kind of like achievements with Frustum PointNet, with VoxelNet, and all the 2D computer vision technique, and we can basically get what is shown here, right? Like you can do semantic segmentation, insight segmentation, 2D detection, and also like 3D object detection, also estimate velocity, very robustly, and you can tune your network to make it run as fast as possible. So here's a video to show the perception components that we have achieved. For example, you can detect, you can classify each of the objects, you can do inset segmentation, and you can do 3D object detection. And you can also combine everything together, and this is some perception system that we built in the early, I think, 2017 or 2018. So after we get this robust perception, so we have a good foundation for the perception part, but the next problem is about trajectory prediction. So again, I think there are some questions in the early days of how we could represent the input for the trajectory prediction problem, especially like the social interaction among all the agents. So one of the typical way, one of the natural way that people can think about for the trajectory prediction is like, some chevron net, for example, from Waymo previously. Basically, you just try to represent all the different map features and also maybe layout and all the agents, the detection information that you can get, and the past history of the Nuro of the ego vehicle and the non-ego vehicle, and you try to predict the future. So you just represent everything in the image domain, and then you try to predict the future. So this is very natural. I think most recently we also published a paper, and actually internally we also derived the similar kind of solutions before, very early, like maybe 2017, 2018, which is also to treat each of those in the vectorized space. Basically, every line segment of the map, we can think it as a 4-dimensional vector, and every agent you can also think as a node with like the position and also history, and you can just using PointNet kind of approach that you project each of those into some high dimensional space, and you apply some operators such as max pooling or some pooling or something like that, and you can extract a feature representation for all your input. And of course, you can also apply some transformer, attention, and all those kind of things to just try to extract better agent-agent interaction, agent-map interaction. And it's a very efficient way. Theoretically, I think, although practically how to make it run as fast as possible, there's still a lot of challenge, because the hardware is heavily optimized for some of the convolutional neural net and some of the graph operation, because you have to customize, implement it. So it's non-trivial, but theoretically it should be much faster. So yeah, this is also some system that we built just maybe in 2018. That was like four years ago, for example. So as here you can see that you have all these cross traffics, and you have like cyclist that is crossing, and as you can see that we have like a multiple hypothesis prediction for how each of the agents is going to move. And this is just a representation of like their future 10 seconds prediction for each of the agents. So finally, after we get this perception prediction, and we want to do planning, and we also ask this question: can we use machine learning for planning tasks? I think there are like some also very obvious way. One is using imitation learning, basically still like fall under the realm of supervised learning. So basically you can do very similar as how you train some of the perception or some of the prediction model, where you go and ask human to drive a lot of like in normal car, and you collect all your observation. You also collect all your action that human take, and you can add that into the training data, and you can just make it as a supervised learning approach, where you just train a neural network to take all the inputs and then trying to map to the output. And you can potentially using like either the rationalization kind of like representation, or using the vectorized representation to encode the input and then trying to predict the outputs. The other kind of potential way to do this planning, because planning is a decision making or sequential decision making process, right? Like, and MTP is kind of like a well formalized solutions for this planning problem. So, and IL is a particular method that can solve this MTP problem very effectively. So, like this is a typical kind of like a IL setting where you have an agent, and then the agent can take certain actions, and the agent interact, take this action, and then run this environment. And usually can be like some simulator or something like that. And the environment spit out like the next state and also the reward for taking that action. And the agent's objective is to maximize the future reward, future discounted reward. And like all the AlphaGo or Atari game are achieved by the breakthrough in reinforcement learning recently. So there are these two different approaches, and in the early days we also have a lot of debates on whether we should use imitation learning or reinforcement learning for the planning tasks for self-driving. So imitation learning. So there are like a few pros. I think it's really very easy to to train a model. You can basically take some of the prediction model that you have and then just convert that into predict on ego vehicle. And you may be having some more information, like where you want to go. So you don't need to guess where like the ego vehicle will go. So because you know that. So it's very easy to learn good low-level trajectory, because you can just see how human drive in the future, and you can just make that as your output. But cons is that I think it's a very common like limitation for imitation learning, especially running that includes loop, is for the distribution shift. For example, like if every timestamp you have some small error and you will compound and you have the stagger issue. So it's very hard to, normally people have to collect some more data to tackle this kind of issue. But in practice, sometimes it can be very expensive and very challenging to collect those data. And also like the loss is to mimic human driving. But sometimes like how human drive is not directly tied to the final gates of how we think whether an autonomous vehicle is safe to deploy. Reinforcement on the other side, it can, the objective is to maximize the future reward. So sometimes you can say like, I want to maximize my progress with constraints of my risk is, or, like my cost is less than some threshold, for example. And you can cast that into some constraint optimization problem. And, it's directly optimized for the final gates. I think like it is also more data efficient because of, you can just have the agents to explore in the environment and then trying to sample data to improve itself instead of like, having people to provide this kind of supervision to learn. And it can potentially also be achieving superhuman performance, as we see in AlphaGo or in many other kind of like applications. But there's also like no free lunch, right? Like it's also very, very hard to train this RL model. It's very hard to debug compared to some of the supervised learning methods. And also a key is that you also need to define reward to shape a good behavior. So it's often in practice, it's also very hard to tune this reward to make the behavior good. There's approaches like using inverse reinforcement learning to learn the reward first from the data and then use this reward to optimize for RL. And I think like what I found and also heard from people saying is like using this inverse RL to learn reward and then train RL to optimize for the learned reward doesn't seem to work in practice in many of the applications. And also like a key challenge is also like it requires a good simulator that we want to model other agents' behavior well. I will talk about, I will touch on this simulator part later, but I think, it's challenging for IL, but it's also challenging for evaluating the autonomous stack. So at Nuro, actually, in the last 3 years, we were spending this effort of building this called Nuro Gym, which was basically a reinforcement learning platform that allows us to play with some of these reinforcement learning algorithms for self-driving. So basically, there are 3 components. You have the learner, which was basically like, have a network, neural network that defines policy, defines the value network, whatever. And the learner is, with objective to maximize the reward. And, during the training, like every once a while, the learner will send the latest network weights to the workers, and we have like thousands of workers running at the back to just have the agents to collect data from the simulation, and then afterwards we send the simulation results back, then store that in a liquid buffer. And in particular here we are doing this offline policy IL, off policy IL. That's to be efficient instead of like doing fully like on policy, which is very expensive and also hard to make the simulator adapt for that case. But we found out using off policy algorithm seems to also work reasonably well, although we don't know what is upper bound if we use on policy data only. I think there's another extreme of like offline IL where we don't allow agents to do any interaction in simulation. And there are also like a lot of work like CQL, IQL kind of work that can potentially be a good strategy to pre-train this policy beforehand using a lot of this onload data or any of the simulated data. So there's like also kind of like open questions. But again, I'm just describing the infrastructure that we built for doing IL for self-driving case. And here I'm just also showing case some results that we got from IL. Maybe also this video is from 1 or 2 years ago, and we have some better results recently. But so here you were just saying like it's a narrow oncoming case, where you have a lot of parked vehicles on the side, and you have like oncoming vehicles, and you want to train the model to navigate safely in the environment. And as you can see, the model seems to learn pretty well. Like it learns to yield to the vehicle, and then also nudge to the right in the gap, and also like try to wait the oncoming to pass, and then it can go afterwards. So I think it's learning something reasonable, and also recently we see some pretty promising results from our But I think safety is a very important part for autonomous driving. I think for every autonomous driving company. So how do we ensure safety? I think for approaches like imitation learning, for example, or any kind of like machine learning model, I would say it's very hard to have hard constraints from the model outputs. It is not a problem. It is not only a problem for imitation learning, but even though if you use some latest methods like diffusion model or any of the energy-based model, whatever, I think it's just very hard to have hard constraints. What I mean hard constraints is like the trajectory should not overlap with a static object, for example. There's no guarantee that the machine learning will output a good solution that exactly avoid collide. So in practice, I think people need to apply some optimization kind of thing afterwards, like MPC, like ILQR kind of thing. For reinforcement learning, as I said, like typical reinforcement learning is formulated as a problem to maximize future discounted rewards. But here safety is very important. So but you can also do this in the constraint MDP kind of setting where you want to optimize for the future reward, like such as progress you can make with the constraints that like your risk is less than some threshold. And it's also like, the safe RL is also quite popular topic recently. And also like, with the concept of risk here, and we want to also have a, good value estimation for the risk accurately. And for particularly for RL safety, I want to mention two papers here. One is called CVPO that was developed internally. I think it's called Constraint Variational Policy Optimization. So basically, the concept is that you have like two things you need to consider for the RL objective. One is the reward, things like progress, how much progress the self-driving car has made. Right, the cost is like the risk of collision or risk of driving too fast around objects, for example. So usually these are the two main conflicting objectives. Like one naive way is you can just do some tuning. For example, like if you collide, you just give -100 to your collision event, and if you make some progress, you get some small positive reward, and you can combine them together, and then just use your favorite RL algorithm to optimize for that. But usually it's very hard to tune that. If people from optimization background, right, like this kind of objective, you can also treat it as using Lagrangian multiplier to combine this, and then you solve this dual problem. And then, but it's non-trivial to solve that. There's some work on like using PID control kind of things to do this constraint optimization. But in this paper, we kind of like propose an alternative approach where we, like basically you have this reward, the positive value estimation, and also the cost, which are the constraints. And you want to learn a policy to maximize reward and minimize cost. And we can basically think that as some linear optimization problem. Like you can apply any kind of like convex optimization to give you a reward, give you a cost, and you try to say what is the optimal solutions for maximizing reward and with constraints of minimizing risk. And after we get this using this convex optimization, we arrive in some variational policy. That is the policy that is the optimal according to the convex optimization. We call it the E step. And then afterwards, we basically, and we need to learn the final policy. And we just, do this M step to just make sure the policy is as close as to the variational policy. So this way, we find it is very effective to decouple these two problems and then try to have this optimization be solved very efficiently. The other one I want to call out is called Recovery RL. I think it's also a recent safe RL paper. So in this particular environment, is like the red dot is agent and the blue walls are the obstacles that you want to avoid. So what it does is like it also decouples the problem into two policy. Normally you have like one policy which is just to, as shown in the above, like CVPO even, you just have one policy. But here in Recovery RL, you have two policy. One policy is that you try to just execute. That was your main policy that we call task policy. The other policy is called recovery policy, which is the one that just to try to prevent you getting to this unsafe state. So what you do is basically you train some network and then you can sample the actions. I mean, here you are just I think the original paper they are operating on the continuous action space. So you sample some actions from the network, and then you have like some evaluation strategy of like estimating, like if you take this action, what is the risk of taking this action? And if the risk of taking this action is very, very low, meaning like less than some manually defined threshold, you will say, okay, the action is safe and you can execute the action. If the action is unsafe, meaning like the risk of taking this action is higher than some threshold, you will say it's unsafe, and you will fall back to the recovery policy. And the recovery policy can prevent you getting to these unsafe states. So through this decouple, it also try to, make this constraint optimization problem easier. So finally, also maybe talk about the open questions for autonomous driving. So, for the perception side, I think, it has a really good foundations on how to solve it, from 2D and 3D. But I think there's also a lot of long-tail perception issues, how to handle those robustly, like, anything could happen in the environment, right? Like, and sometimes it requires some very complex, high-level thing understanding. I don't see any kind of like practical solutions that can handle it very well. Let me know if you know any of those work. I think also on some extreme kind of case where like you have heavy rain or heavy snow, for very very far away objects where you just very very small in camera and the lidar, and also like occlusion, like you just heavily occluded from your sensor. So those are still very challenging. And also there's like also line of work on how to merge all the sensor inputs together. For example, previously I talked about the Frustum PointNet, which is like, doing this camera view of detection, then to 3D PointNet, and VoxelNet is just completely operating on the LiDAR space. There's recent work like DETR 3D, which is basically doing some 3D detection using like transformer with only cameras, and also BEV former, which is also like using transformer to automatically learn to extract features from cameras, from other sensors, to generate features for each of the voxel. For prediction and planning, I would like to put them together because I think they should couple together instead of like perception and prediction. If we try to merge some of the components, I think there's still like some open questions like needs to answer, like, and how do we encode this agent and agent map kind of like interaction more effectively? Because this is about how we represent the interaction. How do we understand the interaction? It's like GPT-3 kind of thing. Like you want to have like some model that can really train in a way that can really enable the model to understand the nuance interaction among all the agents. So how to do it effectively, I think is yet to be seen, and then see how it evolves. But it's definitely a very open questions. I think also the other one I mentioned that should be like joint prediction planning. We should consider both of them together, both problems together, and how to have a joint ML models for prediction planning. That's also an open question. Just normally like the typical way how people solve this problem nowadays, like you first do marginal prediction, and then you do planning based on the marginal prediction. I just don't say that is enough, and also it's suboptimal. Yeah. And finally, the difference between behavior and perception is that perception, you have a perfect loop controls you can compare to, but for behavior, especially like the closed loop behavior, it's just very, very hard to evaluate, making it very, very hard to, develop algorithm, because if you change something, if you change some algorithm, if you change some hyperparameter, you don't know, whether it's improving your system or not. So that's very challenging. And also, even if you have these eval metrics, and eventually we need to deploy in the real world, and how much can we trust the evaluation metrics, and so that we have confidence that we can deploy in the real world, that is still unknown. So this is still like open questions.